Hi guys, Dr. Man is here today. Today we're talking about bonding. Bonding is what you do when you bond atoms together. Bond means to attach atoms together. The way you attach atoms together, or I should say is the way they naturally attach, will be whatever is most convenient for them. Do you staple to get papers together or do you glue them? I don't know, it depends what's convenient. Well, for atoms, what's convenient is what gets them to the lowest energy state. Lower energy states are always preferred. Lower energy states tend to be stable. We already know the most stable elements, the noble gases. So maybe we could look at them. What do noble gases have that other atoms don't have? They have filled energy levels and sublevels. Well, filled energy levels and sublevels are preferred because they're lower energy. So atoms typically react to either fill up or empty out their sublevels and their energy levels. And there are three different ways that they do that. It really just depends upon whether they need to gain electrons. That's the easiest thing to do to become filled, or maybe lose electrons to become filled. Because you can think like, well, the atoms all that are over here close to the noble gases, well, they can just gain a couple of electrons and be full. But like the atoms over here on this side of the table, the metals, well, they need to gain a lot of electrons or more likely just lose a couple of electrons. Like calcium just loses 2 electrons and he's empty. Okay, empty and filled sublevels are stable. They're preferred. So really what's going to happen here depends upon what the atom needs to do to sort of empty out or fill up the energy levels. Alrighty, and really there are just three things that get done. Three types of bonds that we're going to rationalize. One, what happens with these metals? Secondly, what happens with the nonmetals? And thirdly, what happens if you have a blend and you have metals with nonmetals? So let's just get into it. The bond types are going to be ionic, metallic, or covalent. Okay, three main types of bonds. Covalent gets split because covalent is a sharing of electrons, and real three bond types. That's good. Covalent is three different types of sharing. All right, but ionic is ionic, metallic will be metallic. So let's just talk about them first, then we'll dive into the covalent. An ionic bond is just an attraction between a cation and an anion. That is it. Sometimes in middle school, teachers confuse oxidation and reduction, a transfer of electrons, with the ionic bond. The transfer of electrons creates the ions. The attraction of the ions is the ionic bond. A cation, positive, with an anion, negative, opposites attract. Usually the cation's a metal, like in this one we have sodium with chloride, iron with oxide. The anion tends to be the nonmetal, the chlorine, or the oxygen. Okay, anyway, cation and anion makes ionic. So anytime you see a metal with nonmetal, you know you got an ionic compound. If you have only nonmetals in there, odds are it's not going to be ionic. It's probably covalent, which comes up later. Okay, metallic bond is probably the easiest one to identify. In a metallic bond, you basically have metals. All you have is a metal. So if you have a metal rod, it's got to be attached together somehow. Those atoms are fused together somehow, attached somehow. And the reason is the metallic bond. And what that is the valence electrons sort of surround all the atoms. There's a sea of valence electrons. That's what I drew there in green. And the valence electrons are free to meander all around and all over through here. And that's why metals conduct so well, by the way. But the valence electrons are sort of loosey-goosey, but it's all sort of held together because there's one sea of valence electrons. And there you got the metal. Okay, so you got ions for ionic bonding, just metal atoms for metallic bonding, and if you got only nonmetals, you tend to have covalent bonding. Nonmetals need to gain electrons to become stable, and so if you have something that needs to gain electrons with something else that needs to gain electrons, then basically what they do is they end up sharing electrons. Okay, and because the electron is being shared and not taken one way or the other, there are no ions. Okay, there might be some pole, which we'll talk about later, but we just have a sharing of electrons. And so you can identify it like in these examples, you got water, you got ethane and methylamine. They're only nonmetals, CHNO, and so they're covalent. Okay, remember, if you can't remember from the periodic table, things over here to the right of the staircase, those are your nonmetals. Everything else is going to be a metal. Okay, in covalent bond, you basically have an orbital from one atom overlapping with the orbital of another atom, so that if you have an electron cloud with another electron cloud, you get this overlapping space. That overlapping space is a region of space within a molecule, so it tends to be a molecular orbital. So basically what you have is one atom, electron, okay, and the other atom's electron coming together to form a molecular orbital filled with an electron pair. The way you designate that is by saying, hey, these are going to be our molecular orbitals, and the electrons are going to go in them. If you notice, the electrons go from a high energy state down to a lower energy state. That's preferred. Lower energy states are stable, so the formation of that bond should be a preferable gig. All right? And that's a covalent bond. Don't get too caught up in this molecular orbital thing unless you're in AP chemistry. Even then, don't get too caught up. Okay? If the sharing is equal or unequal, that's going to move those electrons back and forth in this little environs. It'll move that electron pair between the nuclei and create some poles. And so we need to look at that a little bit. Okay? Poles are just regions of charge within a molecule. Okay, a pole is a region of charge. If you think of like North Pole and South Pole, they're the ends of that magnetic field. Well, think of a pole as kind of like that. It's the spot where the charge kind of is in the molecule. Kind of like the North Pole is a spot on the Earth. Well, a pole is a spot on the big molecule. Okay, polar molecules have poles. Non-polar molecules, no poles. All right. Things that are polar tend to dig other things that are polar. Things that are non-polar don't. Okay. Like polar things, only non-polar things. That's why like oil and water don't mix, because oil and water are different polarities. Okay. So if you think of this, how do you develop this pole? Okay. The way you want to think about developing a pole is through a tug of war contest between two atoms. Okay. You should be kind of familiar with tug of war. Okay. So when you pull on a rope, got a little flag there. It's going to be pulled one way or the other, and depends upon the strength of our two combatants. If they're of equal strength, then the flag's going to kind of hang in the middle. But if they're unequal, then the flag will move and somebody will win. Alrighty. So let's look at it when they're about equal in strength. Okay, the flag is in the middle. Okay, we're not going to get any movement there, so that's a non-polar thing. If you look at our molecule, there's our shared electron pair, our two nuclei. The electron pair is hanging right in the middle between the two nuclei. There's no buildup of charge anywhere, and so there's no charges being built, so there's no pull, because the electronegativity is about equal. Well, what if they're not equal? What if like this guy is stronger? He's just a stronger person, okay? And he's probably win that tug of war contest and pull that flag over to him. Well, as far as electronegativity goes, well, if this atom is more electronegative, don't worry about how you tell if it's more electronegative. I'll tell you in a second. But if he is more electronegative, then that electron moves that way. And so you have this movement of electrons. Okay, and that's your dipole arrow that I showed up there. All right, the electrons are actually moving from the center closer, more attracted to that other nucleus. Okay, it's all definition of electronegativity, the ability to attract electrons. Well, if one has a greater ability to attract electrons, then those electrons are going to move closer to the nucleus. The electron pair is still between the nuclei. It's still in this region of space within the orbitals. That's okay. But it's just spending more time over to the other nuclei. It's getting more attention. Okay? Because the electrons are drifting to the right, we get a kind of a negative buildup over there. Because it's a gaining electron density. From the spot that's losing it, well, that's a positive. Gaining electrons, negative. Losing electrons, positive. They're not full-blown charges, which is why you have that ugly, there's just a delta. It means partial. Okay, you have slight polarity being built. Those are the poles. Since you have two poles, it's called a dipole. Di means two. Okay, so with all that, whoo, and that was a lot. All right, how can you tell the bond types? Well, ionic bonds are kind of straight up. They're metals with nonmetals. Okay, no big deal there. Like FeCl3, you got the metal atom, non-metal atom. Groovy. Metallic bonds, even easier. Just a metal atom. Okay. If I should back up. It's got to be a metal. Say you had something like, I don't know, helium gas. You have a helium balloon. Okay? Well, that helium balloon isn't a metal. It's a non-metal. And so there are no bonds there. It's a gas. It's just atoms spread apart, not attached to each other. That's why noble gases are gases. Okay? There's no attachment. Okay? So when you see a singular atom, it's probably in this section of your course, it's going to be a metal atom. It'll be metallic. Okay? Pure nonpolar covalent bonds are when you have two nonmetals that are of equal strength. And the only way they're going to be of equal strength is if in that tug of war contest you have two identical people, two identical atoms. So you have the same two nonmetals, pure nonpolar covalent bond. Okay? Then you have the polar versus nonpolar covalent. If there's a tiny electronegativity difference, okay, then it's typically going to be nonpolar. If you have some websites and some people say, well, it's got to be polar because there's a difference. Well, yeah, but practically speaking, if it's a tiny difference, not so much. In a tug of war contest, if they're not equally matched, one guy's just a little bit stronger, probably not going to have enough strength to pull it over his way, though. So we're still going to call those nonpolar. Okay, a larger difference is going to create a stronger dipole. It's going to create more polarity, and we're going to call those polar covalent. Okay, so how can you tell this strength? How do you know the relative electronegativities? Well, you get it from the periodic table. Okay, first, locate the metals and the nonmetals in the periodic table. Second, realize that bunch of the nonmetals don't do anything, so just focus on the ones that matter, that are kind of stable. And of them, since electronegativity increases over and up, okay, we're going to have highly electronegative atoms in that corner. Those are the ones that are strongest. If they are in the corner, then you're going to have a polar covalent bond. Okay, so like look at these. You have two identical atoms, HH, FF, CC. That's a pure covalent bond. But wait, it has an F. Yeah, I said FF is there, but think of your tug of war contest. Two really strong guys cancel each other out. So two fluorine atoms pulling on each other, their regular strengths are going to cancel each other out, and the electron pair is going to sit in the middle and chill and just be a pure non-polar covalent bond. If their differences are just a little bit, not so much, they're not in the corner. They're not the NOFClBr of that corner. All right, but say there's C and H different. Their difference in electronegativity is tiny. It's easy to remember which ones are stronger than all the dudes. They're not. Okay, so we measure H and C are not one of the strongest types. There's not a big enough difference in electronegativity. We're going to call that nonpolar. Okay. Realize that all these bonds would be H and C. Since they're nonpolar covalent bonds, pay attention to where I drew that little set of dots. The groovy little set of dots there. It's in the middle. That's representing electron pairs are equally shared. Okay. Well, with a polar covalent, we're going to look at something like the CO bond or the OH bond, because then we have an O. We have somebody from that sexy little corner of NOFClBr. We got the O. Oxygen is the second most electronegative element on the planet. Okay, so that oxygen is really, really, really going to pull the electrons to it. Alrighty, so if you pay attention to those bonds, that electron pair is skewed over to the oxygen in both cases. And the electrons are negative. So in both cases, the oxygen is going to get that partial negative charge. Okay, and the other end of the bond that's losing the electrons, the other end of the bond becomes partially positive. Those are your two poles. Okay, these dipole arrows down here, it just shows the movement of electrons. So the electrons are going to the oxygen. They're to the oxygen. So it's that, don't get too bent out of shape with those arrows. They're generally just saying where they're going. The arrow points to the more electronegative one. If it helps, the dipole arrow has a plus sign on the back side. So if you look at a plus, like if you look at this, you get a plus and a minus. Make an arrow out of it, make the dipole arrow. Alrighty. If you're worried about how to make those structures, that's coming up next. In my next video, you can check out how to make them. Check it out. It's good times. Take care.